Welcome back to geometry. So this section's on inscribed angles, and this is shorter than 12.2. I think we will get this in one video. So here's a setup. Say we have a circle. This is circle C, the center is C, with a central angle labeled here at 120 degrees. So we've already learned that this must also be 120, which we call the measure of the arc AB. Not the length, but the measure. So the measure of a central angle always equals the measure of its intercepted arc. Always the same. But this section's about inscribed angles. We haven't learned about inscribed angles yet, so let me show you what it is. An inscribed angle is if you were to put like a point D down here, and like that. So angle, I guess I'll write that down. Angle ADB is what we call an inscribed angle. And what do you think it measures? What do you think that angle right there is? Is it 120? Is it 90? Is it more than 120 or less? Or is it equal? It's not equal, right? Because imagine this is like a slingshot or something, and you're standing at C, okay? You have the slingshot stretched. At this point, it's not that tight from A to C and A to B. Now you back up to D. As you do, what's happening to that angle? It's getting smaller, right? It's getting smaller. You're spreading the same width at AB, but you're doing it in more time. You have more time to do it, so the angle is smaller. So it's always going to be smaller than the central angle. Well, that's not very helpful. Smaller. What is it? How much smaller? Turns out it is half. So rather than smaller than, let's change that to half. Half the central angle. Half, should I say, the measure of the central angle. That's really the big idea today. We're going to have two other kind of subtopics, but they all fall under this same idea. So an inscribed angle is always half the measure of its intercepted arc. Write that down. An inscribed angle is always half the measure of its intercepted arc. Okay? Big idea. So that leads us to two more, and really are saying the same thing. And then we'll have just a few examples to wrap this up. And there is one example that's peculiar and surprising we'll need to make sure we cover. Okay, we have a circle. We have a point X and a point Y on the circle. That makes an arc, X to Y. And let's draw some inscribed angles. Draw one like that. They're all going to open to X, Y. You know what? I'm going to change these colors so we can see them a little better. Let's make a red one. We have our blue one, and we'll do a green one. Okay. So, how do the angles at A, B, and C compare? Well, A, we know, angle A, is half the measure of the arc XY. Angle A, measure of angle A equals 1/2 of the arc from X to Y, right? And what's the measure of angle B? Well, it's half the measure of its intercepted arc, which is the same. Measure of angle C, it's half the measure of its intercepted arc, which yet again is the same. So what do we know about these three? They're equal. These are the same. No matter how you draw it, I drew a little one over here, they would all be the same, which is really cool. In my classroom, I have a student who made a figure of this, kind of the back of the class, maybe you've seen it before, they're all the same. That's one of the cooler, really beautiful theorems of geometry. Just you can make some cool designs with that. All those angles open to the same arc, so they are all congruent. Okay? So do we need a theorem for that? I mean, not really. We know that this right here is really the idea. So it's kind of a substitution idea. Let's look at that special case I was talking about a minute ago. Okay, we're going to have, this time we're going to be looking at the arc AB as our kind of featured arc. And we're going to draw some intercepted arcs off it. One, something like this. One, maybe like this. And we know that these, if we call this E and D, we know that those angles are the same. Okay, big deal. We already learned that. We already had that moment of excitement. But what if we did this? What if I did an angle that went from A to B and then was tangent there? How about that angle? Let's put a C here so you know what I'm talking about. The angle ABC. Well, guess what? It is congruent as well. Because what if you had to say what arc does the angle ABC open up to? Right there, it's opening up to the same arc as the other. I mean, what else is it open to? All three of those angles, let me make sure you see them, angle 1, angle 2, angle 3, they all open to the same arc, therefore they're all congruent. So even angle 3, that is comprised of, by the way, I don't think I've mentioned this, we often call this a secant line. So you might say, wait a second, isn't that a chord? Yes, a chord is part of a secant line. The secant line is the full line, infinite length line. The chord is just the segment with its endpoints on this circle. So the angle ABC is made up of a secant line, AB, and a tangent line, BC. So same rules apply. It's half the length of the arc it opens up to, or as the book says, it's the intercepted arc. So be on the lookout for that. That's a tricky one. And our final thing to note here, so what if we look at our intercepted arc being a diameter? Something surprising is going to happen. So what is the measure of this arc? Well, let's just draw a few of these. Let's draw a red one. Whoops, not what I meant to do. Let's draw a red one, a blue one. It's a shame I didn't draw this better. And a green one. So all three of those angles open to the same arc, so they're all the same. Yay, big deal. But more than that, they open up to 180-degree arc. So remember, they're half the measure of their intercepted arc. What's half of 180? It is 90. So these aren't just congruent angles, but they're actually all right angles. Right angle, right angle, right angle. Again, limited by my poor drawing. But we can make this claim. An angle inscribed a semicircle, inscribed inside of a semicircle where the hypotenuse is a diameter, those will always be a right triangle. Let's say that again. So you have a circle. No, let's do a semicircle. You have a semicircle, and you want to make a triangle where one side of the triangle is the diameter of the semicircle. No matter how you draw it, if the third vertex is on the circle, every one of these will be right triangles, regardless of how poorly I represent it. Those are all right triangles. A really neat concept there. Okay, finally, let's do a few examples to wrap this up. These are the kind of problems you're going to encounter. These really this whole chapter, well, with a few exceptions with some quadratics that you've encountered, but these problems really generally are very short. So let's say there's a circle, we have this inscribed angle. An inscribed angle, again, the vertex of the angle is on the circle. So let's say this arc is 140 degrees, and we want to know what this angle is. What is it? 70 degrees is half the measure of its intercepted arc, right? Try another. We have, let's say, this is given as 90, and this is given as 120, and I want to find out what this is. This is a good one. This one's a little tougher. Give you a second to think about it. Okay, so know that if I were to go, you know this, right? All the way around this circle, how many degrees would I have gone? 360, right? So this portion is 90. This portion is 120. What's left for this portion up top? Well, 90 plus 120 is 210, so it's exactly 150 left. It's hard to read that. 150 degrees left. So what's this? 75. Aren't these nice? If this was on a test, drawing that right there, probably the main thing I'm looking for. That you had to find that first, you got that, and then you're able to get X. Two more. This one, I have this kind of interesting setup here. This is 40 degrees. This is Y. And this is X. Well, there's a couple ways you can do this one. Probably the most straightforward way is to say, well, I don't know if the most straightforward way, but one way is to say, oh, Y is 80. Because 40 is half the measure of its intercepted arc. Y, notice it's centered right here, so Y is double the inscribed angle then, right? So that 40 degrees can be half of it. And then X, well, X is half of 80, so X is 40. But you might have also just said, wait a second, these are two inscribed angles that open to the same arc. They're congruent. You could have got the 40 that way also. Okay, last one for 12.3 is this. We have a circle, we have a tangent line. Okay, so that is tangent, we'll say. This line and this angle here is given as 130 degrees. Oh, no. It's not given as 130. Mistake. This is given as 260. Let me write it in black so it maybe looks more evident that it's given. Okay. Notice, remember, a label is centered on the thing it's measuring, so it is measuring that. That's 260. And this question is asking for this angle here. The whole thing, right? That whole angle. Okay, well, there's two ways to do this one. One, maybe the easiest way is to say, I don't know what's the easiest way, but two ways. So one is to note that this angle, as I was wanting to give to you a moment ago, has to be 130. Do you see that that is an inscribed angle has its vertex on the circle? that vertex is on the circle. Yeah, one of the lines is tangent, but that's okay. It's on the circle. So it is 130 degrees because it's half the measure of its intercepted arc. And then just from chapter 1 geometry, we know that this question mark, I guess we call that x, well, why not, is 50 degrees. There's 50 degrees left to make this straight angle. Another way you could have done it, you could have said, this is 260, right? Then what's left for this portion is 100. And then the question mark is actually the inscribed angle that opens up to this green 100-degree arc. And so that would be another way to get that right away. So we know that the question mark must be half of the green intercepted arc, which is 100. And that makes up 12.3. Hopefully that makes sense. Look at the examples in the book. These are kind of hard to do because there's a lot of drawing on my part.